Hey everybody, in this video we're going to be taking a look at how we can use an exponential growth or decay model to, say, model the quantity of something changing over time. And I would say that specifically in this example, we're going to be looking at what we call radioactive decay. And so it is the case that certain radioactive isotopes, they tend to decay in their mass over time. And so one thing we tend to look at is the half-life of some amount of radioactive substance. So when we talk about half-life, that's kind of where I want to start. We refer to the half-life is an amount of time, okay? And specifically, it's the amount of time that needs to pass for the initial amount of material to diminish by half of its original amount. So it's kind of like this. If I put 6 Cokes in the refrigerator at the academy and I leave them in there and I kind of check on them throughout the week, I notice that maybe after Monday, like somebody took one of my sodas there. And then after Tuesday, nobody took a soda. After Wednesday, somebody took 2 sodas. And then, I go in there, I check on Wednesday, I noticed that half of my sodas were gone. So if the week started on, say, Monday, it was a 3-day half-life for my Cokes. So here's the deal. If what we're looking at is half-life of a radioactive isotope, then each radioactive isotope is going to have its own kind of like half-life here. So I'm going to read through and we're going to take a look at this model that we give here as an exponential model and then use our model to kind of answer some questions, especially using our graphing calculators to help answer. So it's going to say, let Q represent the mass of radium-226. So we write that as 226 Ra. And we say whose half-life is 1620 years. That means that if you started with 10 grams of mass, okay, it would take you this many years just to become 5 grams of mass left over. So they give us this model. It says the quantity of radium present after T years is given by Q of T, or mass as a function of time, is given as 16 times the half to the power of T over 1620. Now this is pretty common that you're loaded up with a model here. And you're like, what? What does this all mean? I'm not really sure how to read this. But some things I do want to talk about are just identifying your variables. The y variable here represents the mass of something, and t is going to represent the time at which we're finding our different masses here. So you can really look at q of t and t as really being kind of like y, and I suppose in this case here, our t would become an x to the power of x over 1620. So with respect to our model, what I want to do is kind of just take a look at what's happening to the amount of this material over time. So I write here, sketch the graph of the function over the interval from t equals 0 to t equals 5,000. So we're going to bust out our calculators here, make sure they're turned on, and what we're going to do is we're really just going to table some values. So if I said from 0 to 5,000 I want to make a sketch, then maybe what I need to be doing is making a table of values here. So I'm going to say time and the amount of radioactive isotope at that time, and if I'm going from 0 to 5,000, I'm kind of inclined to go by like 1,000 year increments just to get a good idea of what this is changing by. So we would say from 0 to 5,000, if we were to table some of these values here, it's as easy as saying that we have 16, in parentheses we had 1 divided by 2, and this is all to the power of our x value over 1620. So in our first case, we'd say 1,000 divided by 1620 would be our exponent. I'm going to hit enter, and I'm going to say this is how much material would be left at 1,000 years later. Now 10.43, I'm going to say this is 10.43 grams, in which we are measuring the radioactive isotope here. I noticed that I didn't put grams in the problem there, so I apologize. One that I didn't test for, and what I should test for right now, is what happens when we plug in 0. So I'll actually show my work on this one. We get 16 times a half to the 0 over 1620, and 0 over anything not 0 is really just 0, so we get 1/2 to the 0. 1/2 to the 0 is really 1. So in other words, we get 16 here. This is significant because we're saying that at time 0, initially, we had 16 grams of material. So at least with our models, with respect to our models, this number that you see out here, this what we traditionally call an A value, is our initial amount. So after 1,000 years, we're down to only about 10.43 grams of this. Let's go ahead and hit second enter, and we're going to go back and we're going to switch this to 2,000 years. 2,000, second enter. I'm going to go back and switch this to 3,000. We might as well get a couple of these at a time. So at 2000 we had 6.80-ish, so 6.80 grams. At 3000 we have 4.43 grams remaining. At 4,000 and 5,000, let's go ahead and evaluate for these as well. We've got our graphing calculator here. So 4,000, and we'll hit second enter. We'll go back and switch that 4,000 to 5,000. So we can see that 2.89 and 1.88, 2.89 and 1.88. The idea is that we want to make a sketch of this over time. So if we are going to sketch what we put in our table here, let's go ahead and get our first quadrant sketched out here. It is important that we are labeling these values here on our sketch. So first things first, we're going to put time as our independent variable here. And so I'm going to say time. And since it's in years, we're going to label this. And up here, we're going to say mass of the isotope, and we're going to say that this is in grams. Now, what I should put on my x and y axis depends upon what we put in our table. So if this is 0, I'm going to say that this is 1,000, 2,000, 3,000, 4,000, and we'll call this one 5,000. So I can label my scale on just one of these notch marks. And then here we went up to, at least the most I ever saw was 16 grams. So maybe what I need to do is say 5, 10, 15, and we'll say that this is 20. We can call this one a benchmark here, 10. So to graph what we have, we started at 0, 16, which was this point right here. We said after about 1,000 years, we're a little bit above 10 grams. After 2,000 years, we're at about 6.8 grams, so almost 7. After 3,000 years, we're under 5 grams. We're 4.43, so here. After 4,000 years, we're 2.89, so a little bit above 2.5. And then after 5,000 years, we had this 1.88 left. So you can see that this isn't a very rapid decay. As a matter of fact, shoot, it takes 1,620 years just to be cut in half. So as we look at this, letter B says determine the initial quantity when t equals 0. Usually what I'm not going to write is the t equals 0 part. And I'm just going to write determine the initial quantity. When I say determine the initial quantity, the question we need to ask is, am I looking for a y value or an x value here? And so in this case, if I say determine the initial quantity, we're looking for a y value. That must mean that I'm implying a time. So whenever you see initial, we're going to imply that the time is 0, right at the beginning of this experiment. So we're going to say q of 0 be equal to 16 times a half to the 0 over 1620 power, which gives us 16. And I just wanted to reflect on this, that our y-intercept of our graph is always going to represent, I'm going to write this here, this is our initial amount of something. And that's always very true with modeling and using exponential growth and decay. This says determine the quantity present after 1,000 years. So again, we're determining the quantity. I'm giving you a time. We're going to plug in 1,000 here, and what we end up with is just something that we had tabled in the first place when we graphed this, when we sketched our graph here. So we got approximately 10.43 grams. Now, for part D, it says use the graph in part B to estimate the half-life of radium-226. Now, the thing here is we were told the half-life of radium-226 to begin with, but how could I use a graph to assess this situation here? So I'm going to change my colors. I'm going to say, well, initially we had 16 grams of material right here. So half of 16 would be 8. I know that that's roughly right about here. So if we were to draw in the line y equals 8. Let the amount equal 8. We could also say the amount at time t equals 8. Then what was the t? We could say if you trace this out to your graph right here, I would say that it's a little beyond 1,000 years. Now my graph is not the best graph ever made. So if I had made this middle portion just a little bit differently or put my line somewhere else, maybe I'd say right here. But we happen to know that it's at about 1,620 years. But at least this graph would give us a way to kind of estimate that value. So some things. In terms of reading models, okay, and how that works, I would say that we tend to be in the practice of, oh, my pen's going crazy here. We tend to be in the practice of identifying what the variables represent. And as you navigate this stuff down here, just keep in mind, what is it that I'm asking for? Am I asking you for a y and I'm giving you a time? Or am I asking for a time and I've given you an amount, okay? But we can just kind of plug and chug with our model and get a good sketch of it. Cheers.